Welcome to our lecture for Lesson 6. Lesson 6 is talking about trajectories, and we got a lot of vocab in this. There's not a whole lot to this lesson, so it should go pretty quickly. Let's get started. To start, a vector field in 3D is just like what you studied last year, a slope field in 2D. Let me change that. The vector field shows, no surprise, the vector at various points in a given range. Okay, a trajectory in our vector field is what you learned last year, like a solution curve. Solution curve in a slope field. Okay, in this lesson, you've been estimating whether flow of a vector field along a curve is clockwise or counterclockwise. You also have estimated whether the flow across the curve is inside out or outside to in. To determine the flow across, you're going to use the normal components of the vector field, and to determine flow along, you're going to use the tangential components of the vector fields. All right, when you're doing this wording, make sure you're very specific. I know most of you are, but just be as specific as possible. Okay. So here we have a question. We see 3 fields here, and we want to know which one is the actual field, which one's a normal field, which one's a tangential field. It's pretty obvious that the middle one there is the normal, and that the last one, the green one over there, is the tangential, which means that the first one, the blue one, must be the actual field, the combination of the normal and the tangential. And it says, why wouldn't it be accurate to state that the flow of this vector field along this curve is counterclockwise? Okay, so we're talking about along the curve, flow along, you should be looking at the tangential graph because of the flow along. Okay, so if you look at the tangential, you want to look at, all right, are more of them clockwise or more of them counterclockwise? And sometimes it's pretty hard to tell, but this one, it looks pretty simple that there is not only more, there's more of these vectors that are pointing in the clockwise direction, but also the clockwise ones are a lot longer too. So we can definitely say that more vectors are pointing in the clockwise direction. So therefore, we can probably say with pretty good confidence here, the net flow of this vector field along this given curve that we have is clockwise. So here we have a dot plot. We want to figure out, all right, what is this dot plot of? So this dot plot, if you look right here, is a dot plot of some field and the normals. And as soon as you see that it's the normals, you should be thinking, all right, this is flow across. All right, we know that this curve is parameterized in the counterclockwise direction. That's just given to us here. So let's interpret this plot. All right, so first thing we can see is that where this graph is positive and negative, it looks like it's positive in the 2 pink areas that I've highlighted, and then negative in the orange area that I've highlighted. So we can say, I'm just going to write estimates here, from 0 to approximately, let's say, 2.6, and also from approximately 4.3 to, let's say, 6.3, our net flow is going to be inside to outside because the dot product is positive. But then from 2.6 to about 4.3, our flow is going to be outside to inside because the dot product is negative. So what does that mean? Well, that means that if you look at this and big picture, there's way more space here that the flow is inside to outside. So we would say that the net flow must also be in the out of this random field across whatever curve that we are looking at. All right, and then the second one there, looking at, first we're looking at this. That is the tangents, the tangential, which then tells us this must be flow along whatever curve we are looking at. All right, so again, we know this curve is parameters in the counterclockwise direction. Let's interpret this plot. So first, let's talk about, all right, this looks negative and this looks negative. So if I was going to estimate those numbers, let's say 0 to 1.2 and also 3.1 to 5.1 is negative, which means that must be clockwise. But these areas are positive, so just kind of making up numbers here. About 1.2 to 3.1, and then 5.1 to 6.3 is positive dot plot, so that means that this must be a counterclockwise flow along. And it looks like those two are going to cancel each other out. So overall, I would say that the net flow along of this vector field across whatever curve we're looking at here must be 0. All right, that's pretty much it. A couple hints there. You can read that hint on the literacy sheet L10. And then another hint on number 11. Can two trajectories of a field ever cross over each other like this is a question you're supposed to answer. What I want you to think about when you're answering this question is, what would happen when the blue field gets there, or the red field gets there, or the red trajectory, the blue trajectory get there? What would they do at that point? So think about that when you answer that question. And that's all for lesson 6. Thank you very much.